The National Electrical Code, or NEC, does not explicitly mandate a ground rod at the pull box near a street light fed by a service pedestal 50 feet away. However, the NEC does offer general guidelines that influence this type of installation. NEC Section 250.52 C2 states that service equipment must be grounded by connecting it to a grounding electrode system, as outlined in Section 250.46. Grounding electrode systems, defined in NEC Section 250.52. 8.1, include various types of electrodes, with ground rods being one of them. NEC Section 250.50 provides general requirements for grounding electrode systems, emphasizing that these systems must be installed and maintained to ensure electrical continuity. Considering these NEC provisions, while a specific ground rod requirement at the pull box doesn't exist, the general emphasis on grounding electrode systems suggests that installing one is a prudent approach. A ground rod at the pull box contributes to electrical continuity and offers an additional grounding path for the street light and its electrical components. Local codes or ordinances might introduce further requirements beyond the NEC. Consulting local authorities will clarify any supplementary stipulations. Therefore, requiring a ground rod based on your established standard aligns with enhancing the electrical safety of the street light and its electrical infrastructure. Let's delve deeper into the specifics of grounding and how it relates to electrical safety. Grounding, at its core, is the process of creating a low impedance path for fault current to return to the source. This path allows overcurrent protection devices, like circuit breakers or fuses, to quickly trip and energize a circuit in the event of a fault. A properly grounded system minimizes the risk of electrical shock and fire hazards. Now let's explore the components of a grounding system. Firstly, the grounding electrode conductor connects the service equipment to the grounding electrode. The grounding electrode itself can be a variety of things, including a ground rod, a ground ring, a metal underground water pipe, or a concrete encased electrode, often referred to as a UFA ground. Secondly, the equipment grounding conductor provides a path for fault current from the equipment back to the service. This conductor is typically a wire, but it can also be metal conduit or other approved raceways. Thirdly, the bonding jumpers connect different metal parts of the electrical system together to ensure they are at the same electrical potential. Now let's examine the NEC requirements for grounding electrodes in more detail. According to NEC Section 250.52, the grounding electrode system must consist of one or more of the following electrodes. Firstly, a metal underground water pipe that is in direct contact with the earth for at least 10 feet. Secondly, a concrete encased electrode consisting of at least 20 feet of bare copper conductor no smaller than 4 AWG encased in at least 2 inches of concrete that is in direct contact with the earth. Thirdly, a ground ring encircling the building or structure consisting of at least 20 feet of bare copper conductor no smaller than 2 AWG buried at a depth of at least 2.5 feet. Fourthly, rod and pipe electrodes, which must be at least 8 feet long and driven into the earth to a depth of at least 8 feet. When using rod or pipe electrodes, the NEC requires that the resistance to ground do not exceed 25 ohms. If the resistance is greater than 25 ohms, an additional electrode must be installed. The size of the grounding electrode conductor is determined by NEC Table 250.66, which is based on the size of the service entrance conductors. The grounding electrode conductor must be securely connected to the grounding electrode using approved methods such as exothermic welding, listed lugs, or other approved connectors. Now let's turn our attention back to the specific scenario of a street light fed by a service pedestal. While the NEC doesn't explicitly require a ground rod at the pull box, there are several reasons why it is a good practice. Firstly, it provides an additional path to ground in case of a fault. If the primary grounding path fails, the ground rod at the pull box can provide a backup path, reducing the risk of electrical shock. Secondly, it helps to equalize the potential between the street light and the surrounding earth. This can reduce the risk of stray voltage, which can be a hazard to people and animals. Thirdly, it can improve the performance of surge protection devices. Surge protection devices divert excess voltage to ground, protecting sensitive electronic equipment from damage. A good grounding system is essential for the effective operation of surge protection devices. Now let's discuss the installation of a ground rod at the pull box. The ground rod should be at least 8 feet long and driven into the earth to a depth of at least 8 feet. It should be located as close as possible to the pull box. The grounding electrode conductor should be connected to the ground rod using an approved connector. The size of the grounding electrode conductor should be determined by NEC Table 250.66 based on the size of the service entrance conductors. The grounding electrode conductor should be protected from physical damage. It should be run in conduit or otherwise protected from being damaged by lawnmowers, vehicles, or other equipment. Now let's consider some additional factors that may influence the decision to install a ground rod at the pull box. Firstly, the soil conditions. If the soil is very dry or rocky, it may be difficult to achieve a good ground connection. In this case, it may be necessary to use multiple ground rods or to use a different type of grounding electrode, such as a ground ring. Secondly, the presence of other underground utilities. Before installing a ground rod, it is important to check for the presence of other underground utilities such as gas lines, water pipes, and communication cables. Contact the local utility companies to locate any underground utilities in the area. Thirdly, local codes and ordinances. As mentioned earlier, local codes and ordinances may have additional requirements for grounding. It is important to check with the local authorities to determine if there are any additional requirements or restrictions. Now, let's discuss some common misconceptions about grounding. Firstly, the misconception that grounding is only necessary for safety. While safety is the primary reason for grounding, it also has other benefits, such as improving the performance of surge protection devices and reducing the risk of stray voltage. Secondly, the misconception that grounding is the same as bonding. Grounding and bonding are related, but they are not the same thing. Grounding provides a path for fault current to return to the source, while bonding connects different metal parts of the electrical system together to ensure they are at the same electrical potential. Thirdly, the misconception that a ground rod is all that is needed for a good grounding system. A ground rod is an important part of a grounding system, but it is not the only component. A good grounding system also includes a grounding electrode conductor, an equipment grounding conductor, and bonding jumpers. Now, let's summarize the key points of this discussion. The NEC does not explicitly require a ground rod to pull box near a street light fed by a service pedestal, but it is a good practice for several reasons. It provides an additional path to ground, helps to equalize the potential between the street light and the surrounding earth, and can improve the performance of surge protection devices. When installing a ground rod, it should be at least 8 feet long and driven into the earth to a depth of at least 8 feet. The grounding electrode conductor should be sized according to NEC Table 250.66 and protected from physical damage. Consider soil conditions, the presence of other underground utilities, and local codes and ordinances. Remember that grounding is not just about safety, but also about improving the performance and reliability of electrical equipment. A well-designed and properly installed grounding system is essential for protecting people and property from electrical hazards. The purpose of grounding is multifaceted. Firstly, it limits the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines. Secondly, it stabilizes the voltage to earth during normal operation. Thirdly, it facilitates the operation of overcurrent protection devices in case of a ground fault. The requirements within NEC Article 250 aim to create a low impedance path for fault current, ensuring that overcurrent devices operate quickly and safely. This minimizes the risk of electrical shock and equipment damage. Grounding electrode systems can consist of various elements, including metal underground water pipes, concrete encased electrodes, ground rings, and ground rods or pipes. The NEC outlines specific requirements for each type of electrode to ensure its effectiveness. For instance, ground rods must be at least 8 feet long and driven into the earth to a specified depth. The resistance to ground is also a critical factor, with a maximum resistance value specified in the NEC. Bonding is equally important as it connects all non-current carrying metal parts to create an electrically conductive path. This ensures that all metal components are at the same electrical potential, reducing the risk of shock. Bonding jumpers are used to connect metal enclosures, raceways, and equipment together. The size of bonding jumpers is determined by the size of the circuit conductors. The equipment grounding conductor EGC provides a path for fault current to return to the source. The EGC can be a wire, a metal raceway, or other approved means. The size of the EGC is determined by the size of the overcurrent protection device protecting the circuit. Ground fault circuit interrupters GFCIs are essential safety devices that protect against electrical shock. GFCIs monitor the current flowing in a circuit and quickly trip if they detect a ground fault. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Now let's revisit the situation with the street light and the pull box. The local requirement for a ground rod at the pull box, even though not explicitly mandated by the NEC, likely stems from a desire to enhance safety and ensure a reliable grounding path. The additional ground rod provides redundancy, offering an alternative path for fault current in case the primary grounding path fails. This is especially important in outdoor environments where conditions can be harsh and unpredictable. The presence of a ground rod at the pull box also helps to minimize voltage gradients in the surrounding area. Voltage gradients occur when fault current flows through the earth, creating a difference in potential between different points. These voltage gradients can be dangerous, as they can cause electrical shock if a person or animal comes into contact with 2 points of different potential. By providing a low impedance path to ground, the ground rod helps to reduce voltage gradients and minimize the risk of electrical shock. In addition to safety benefits, the ground rod at the pull box can also improve the performance of the street light. A well-grounded system helps to reduce electrical noise and interference, which can improve the efficiency and lifespan of the street light. It also provides a stable reference point for the electrical system, which can help to prevent voltage fluctuations and other problems. Now let's consider the specific requirements for installing a ground rod. The ground rod should be made of a conductive material such as copper or galvanized steel. It should be at least 8 feet long and driven into the earth to a depth of at least 8 feet. The top of the ground rod should be flush with the ground or slightly below grade. The grounding electrode conductor should be connected to the ground rod using an approved connector. The connector should be listed for direct burial and should be installed according to the manufacturer's instructions. The grounding electrode conductor should be sized according to NEC Table 250.66. It should be protected from physical damage by being installed in conduit or by other approved means. The location of the ground rod should be chosen carefully. It should be located in an area where the soil is moist and conductive. It should be located away from other underground utilities such as gas lines and water pipes. It should be located in an area where it is not likely to be disturbed or damaged. Finally, it is important to inspect the grounding system regularly to ensure that it is in good condition. Check the ground rod and the grounding electrode conductor for signs of corrosion or damage. Test the resistance to ground to ensure that it is within acceptable limits. If any problems are found, they should be corrected immediately. In conclusion, while the NEC does not explicitly require a ground rod at the pull box near a street light, it is a good practice that enhances safety and improves the performance of the street light. The local requirement for a ground rod is likely based on a desire to provide a redundant grounding path and to minimize voltage gradients in the surrounding area. By following the recommendations outlined in this discussion, you can ensure that the street light is properly grounded and that the electrical system is safe and reliable. Grounding is a fundamental aspect of electrical safety, and understanding the principles and requirements is crucial for anyone working with electrical systems. Remember to always consult the NEC and local codes for specific requirements and to seek guidance from qualified professionals when needed. The installation of a ground rod at the pull box represents a proactive measure to bolster electrical safety and system reliability, aligning with the overarching principles of the NEC and sound engineering practices.